A diode is a two-terminal electronic component that only conducts current in one direction and block currents in the reverse direction. And when the third layer is added to a semiconductor diode, a bipolar junction diode is produced, which is a bipolar junction transistor is produced, which is used for many electronic circuits. So let us start to discuss about the logic gate. Logic gate is the simplest digital circuits are called logic gates. The simplest digital circuits are called logic gate. The logic gates are building block of a digital electronics. Each logic gate made of many microscopic transistors connected together inside a thin slice of silicon. They are used in digital electronics to change one voltage level, that means input, into another output voltage level according to some logical statement relating to them. The logic gate may have one or more inputs, but it has only one output. The logical statements that logic gates follow are called Boolean expression or Boolean algebra. So the Boolean algebra has three forms. The first one is the addition. The first one is addition, and this one is assigned to for an OR gate. So the Boolean expression for all OR gate is y is equals to a plus b for OR gate. What about for that of the AND gate? The AND gate can be represented by a multiplication sign, which is referred as a AND Boolean algebra, and this can be expressed as y is equals to a dot b, which means the AND gate, which match with the AND gate. And the last one is the minus sign. In Boolean expression, we have a minus sign. This one is to represent the NOT gate. The NOT gate. And it can be represent y is equals to a bar, which means in mathematics it is called that is negation, but for physics y is equals to a bar to represent the NOT gate. The other one is the OR gate, AND gate. The OR gate, AND gate, and NOT gate are collectively known as the basic logic gate. And the other, if we combine this AND gate and OR gate, AND gate and OR gate, we get the universal logic gate. That are, if we combine NOT with OR, we get NOR gate, which means NOT OR. And if we combine NOT gate with AND gate, we got NAND gate, which means NOT AND. And collectively we call this one is universal logic gate. Let's see these are one by one. The first one is OR gate. OR gate is a parallel switch. A parallel switch. And when one is used in this case for on or high value or high voltage, and off is used in the place of 0, or we can use 0 for off, which means low value or small value, or there is no current, in other words. From Boolean expression also we can have, as stated previously, we can have OR gate y is equals to a plus b, which means the value of a and b, or the input value for logic gate we have 0 and 1, or high and low. For this case we have 1 and 0, so we can have the symbolic representation and truth table for the OR gate in the following slide. So this one is the representation for OR gate, and this one is how it look like is a circuit simple, and this one is a truth table. Let's see what the truth table is. The OR gate can be 0 only when the value of A and B is 0 or both off. You can look from the circuit diagram. If we off both values, we do not get any light, which means the output value is 0. The other one, if one of them is 1, we get, or the bulb can give a light, then the output will be positive or the output will be high, which means 1. So let's see one by one. If A is 1 and B is 0, the output will be 1, because if I open this one and if I close this one, then I can have a light, because when the electric current is flowing in this direction, so it can two alternative. If I switch one, it can transfer or it can flow with the other sides. So this can be for OR gate. And also if A is 0, which means if A is off and if B is on, we get a light also. Or the bulb will give light where you can get the positive output. And the final one, if both are on, we get a positive value or maximum value, or it gives a light. So this is how we can understand the OR gate. So what is the application of OR gates? In most electronics, we can have OR gate, but let's see one application. An OR gate can be used to feed two light switches for along a dark corridor, which has one switch at one end of the corner and one switch on the other corner. Each of the switch sends an output 0 to the control unit of the no one has pressed the switch. So this is one application. Since to avoid the dark, we use this OR gate. And second gate is AND gate. The simple AND gate is also 2 input and 1 output, and it is a series switch. Remember that OR gate is a parallel switch, but AND gate is a series switch. Output is 1 only if both inputs are 1 for AND gate. Then we can represent this one Boolean expression y is equals to A dot B, as I have said previously. Then you can see this in the symbolic representation. This symbol represents the AND gate, and it is a series switch. So the output is 1 only when both input is 1 or when both a switch is on. The other will have 0 value or no current flow if either one is off. So if we take that is, if both A and B are 0, the result will be, or the output will be 0. The next one is application of AND gate. An AND gate can be used to feed an automatic circuit to lamp up a display in an aeroplane if 2 toilets are in use. So this is to whether a person is present or not in the toilet. We use that is an application of AND gate, because the inside, if the inside is on, the outside also on. So that indicates there is a person inside the toilet, or that some person is in the toilet. So this is one application of the AND gate. So the next basic logic gate is NOT gate. The NOT gate is a 1 input and 1 output logic gate. It inverts or complement the input A to give output Y. So from Boolean's expression, we can have Y is equals to A bar, or the negation of A is, or the opposite output. So this gate is most of the time called inverter, because it inverts the input to the opposite output. Due to this one, equal is inverter. So the symbolic representation for NOT gate is this one. It is 1 input and 1 output. And truth table can be given by, if we have the input 0, the output will be 1, and if we have the input 1, the output be 0, which inverts the input. The application of the NOT gate is so in activating the pipe or using a sensor, a certain sensor. In addition to this one, we can activate waters when the soil is dry. So if the soil is dry, it will needs a moisture, so it will open the pipes, or it will act as opening of the pipe. So let's see the universal logic gates that are the combination of NOT gate and the other basic gates. Combination of OR gate followed by NOT gate gives us NOR gate or NOT OR gate. From the Boolean expression, we can have y is equals to the bar of a plus b. This shows that the result or the output of NOR gate is the reverse of the OR gate. Then the function of this gate is inverting or reversing the output of OR gate. So the next one is NOR gate representation in circuit and truth table. If you look at the NOR gate, can be expressed or can be represented symbolically in two ways. You can show the AND gate and the NOT gate connected together and separately, but we can show with one symbol. Please look at this one. It is different from the OR gate. There is a circle here to indicate the logic gate is NOR gate. And if you look at the truth table, this one is for the first figure and this one is for second diagram or symbol. Both are the same, except here we have R to one step, then this one is eliminated that step. If we look at this output, all are the reverse of OR gate. For example, the first one, A or B is 0, output 0, and if we connect this one with NOT, the output is NOT 0, which is 1. If we look at this one, 1 or 0 is 1. If we connect or if we use this one for the input of NOT gate, we get 0 value. The same thing is for the third and the fourth one. So this is how we can represent or how we can use the NOR gate in representation and the tables, the truth table. And the second one is NAND gate or NOT AND gate. A NAND logical gate is logic gate in which an AND gate followed by a NOT gate. Then the symbol of this one is shown in the following figure, and this one have the result, which is the reverse of the AND gate or the inversion of the AND gate. Let's see the symbolic representation. Again, we have AND gate and followed by NOT gate, which is NAND or NOT AND gate. Or we can represent using this symbol. This arrow or circle represents there is a NOT gate in AND gate. And the truth table is the reverse of the AND gate, because we are invert the output of AND gate. When the inputs are both are 0, 0 and 0 is 0, then NOT 0 is 1, which is inverted. For the case of 1 and 0, the result is 0, NOT 0 is again 1. And something for 0 and 1. And finally, 0 and 1 and 1 is 1, NOT 1 is 0. So this shows that the truth table for NAND gate or NOT AND gate. These are some about the that of the logic gate for basic logic gate and for that of the universal logic gate. Let's do some examples concerning the logic gate. The first example is said that given below are 4 logic gates. Simple. This, those 4, or, nor, and NAND are respectively represented by which of the following? So look at this one. This is OR gate. This one is OR gate. And second one is this is AND gate. AND gate. And the third one is, look, there is a circle here to represent there is NOT gate is added to OR gate. That means this one is NOR gate. NOR gate. And the last one is, again, look, this circle which represents or which indicates the information there is a NOT gate with the AND gate, which is NAND gate or NOT AND gate. NAND gate. Then, based on this idea, the correct answer is C. One is OR. So this can be, by the way, capital. One is OR, yes, and the third one is NOR, which is matched with the required one, and the fourth one is NAND, which is matched with the last one. So the correct answer is C. Let's do again additional example. Example 2. For the given combination of gates, if the logic status of input A, B, C are as follow: A is equals to B is equals to C is 0, and for the case that is A is equals to B and A is equals to B is equals to 1 and C is equals to 0. So for these two situations, which one of the following is correct output? Let's see for the first one, when the 3 inputs are 0. If this one is 0, 0, the output 0 or 0 is 0. If C is 0 again, this will be 0, 0 and 0 is 0. Since this is NAND gate, not 0 is 1. So the first case, the first one is becomes 1. Let's see for the second case. A and B are both 1 and C is 0. So that means 1, 1 and 1 or 1 is gives 1. And C is again 0, 1 and 0 is 1. Not 1 is, because this one is NAND gate, not 1 is, sorry, not 0 is 1. Since this one is 1 and this is 0, 1 and 0 is 0, then not 0 is 1. Then for both cases, we have got 1, 1. Then the answer is for this question is D. The correct answer is D. So let's see an exercise concerning this one. Which gate is represented by the following figure or this figure? A, NAND gate, B, AND gate, C, NOT gate, D, OR gate. The correct answer is A, NAND gate. And second example, second exercise, to get an output 1 from the circuit shown in the figure, the input must be A is equals to 0, B is equals to 1, C is equals to 0, A is equals to 1, B is equals to 0, C also is equals to 0. C, A is equals to 1, B is equals to 0, C is equals to 1. D, A is equals to 1, B is equals to 1, C is equals to 0. Therefore, the correct answer for this one is C. For the case of C, we can get the output 1. Okay, students, let us see exercise 2. To get an output 1 from the circuits shown in the figure below, values will give. If you substitute for A, for B, for C from the choice, then which choice will give you the output 1? So if you check one by one the value of A, the value of B, the value of C in the given logic circuit, and you will get the answer will be C. And check the result, please, students. So this is what we have for today. Let's summarize what we have discussed in this lesson. The logic gates are a building block of digital electronics. The OR gate, AND gate, and NOT gates are called the basic logic gates, and the NOR gate and NAND gate are called the universal logic gates, because any logic gate can be made from the combination of NAND or NOR gates in general. So this is what we have for today.